This is a revision lesson on astronomy. Okay, so I promised you guys that I would have a look here at astronomy that you did all the way back in first year. And we're going to focus here on a few different aspects today. Really, we're just going to look at the celestial bodies today. We're going to look at space. We're going to look at space exploration. We're going to talk about the different planets in detail and what you should know. Okay, so you all should be able to achieve all of these learning intentions. You should be au fait with all of these. Okay, so astronomy, what is it? Okay, what is a celestial body as well? You need to be able to define that. You need to be able to explain all of the planets. Rather, you need to talk about the order of the planets from the sun, and just talk about a few properties of each of those planets. Okay, so you've all probably got a good bit of background knowledge on space now at this moment in time, and this, we see many representations of the solar system, our solar system. Okay, and it's really important to highlight here, any solar system we, represent here in front of us is very much out of scale. Okay, we're talking about enormous distances here between planets and enormous, planets as well, like Jupiter, for example, the biggest planet in our solar system. And you're talking about a planet that's maybe 10 to 15 times bigger than planet Earth. Okay, so you're talking about huge planets. So astronomy here, this branch of science here, is all about the study of celestial bodies. So what is a celestial body? A celestial body is any object that's found outside of our own atmosphere. Okay, that would be considered celestial body. So celestial suggests here that you're looking up at space. Okay, so in terms of the history of astronomy, you should be aware here of two different fields of view here on astronomy. That two views that clashed back in the day. Okay, that was the geocentric model of the solar system and also the heliocentric model of the solar system. So this guy here, Copernicus, was a key astronomer here who discovered that that in fact the Earth orbited around the Sun. Okay, and that was called the heliocentric model, and that the geocentric model was incorrect, and the geocentric model, which was what was believed at the time prior to 1532, was that the sun orbited the Earth. Okay, and this is one of the examples of scientific discoveries that I would ask you to learn off, because it's a very interesting one. We're all familiar with the fact that the Earth orbits around the sun, but historically that was not believed to be the case. And the question that you must bear in mind then is, like, was it worth it, or like what was the value of the research that was done by the astronomers back in the day if they got it so wrong? And of course their work was not all redundant. The astronomers' work, if they hadn't produced so much work prior to that, then maybe Copernicus wouldn't have discovered what he discovered. Now, obviously, he had the benefit of better technology. And how does technology develop? Only with scientific discoveries. Okay, so that would be, I suppose, an important lesson there to learn about how science develops over time. So a celestial body, there's many different types of celestial bodies out there that you need to be aware of. Okay, like in our own solar system here, we've got the planets. So we've got our 8 planets, and the dwarf planet there would include Pluto. And we have also got other things like, for example, moons. Okay, I suppose classically we would know that we have the moon, which is the one moon that orbits the Earth. But for other planets, like for example, Saturn and Jupiter, they have many moons. You're talking about over 100 moons in both cases. So that kind of highlights the fact that the number of moons that orbit a planet always differs. We have asteroids, of course. You'll be familiar with asteroids and the story of the dinosaurs. Meteors, and there's different branches of meteors as well that you need to be aware of, and comets as well would be important. What else is there that we're going to spend less time on? Dwarf planets like Pluto. Satellites, so orbiting our own planets. So like there's natural satellites, like for example the moon, and there are robotic satellites that we ourselves put up. into space. Okay, so all of your broadband and all of that is provided for by satellite technology. We've also got lots of space junk that is just floating around in space as well. And we've got an International Space Station, which is kind of provided for by NASA and other international space companies. Okay, um, so if we talk here about the planets, first of all, okay, you might know here that the sun, like the order of the planets from the sun, starts with Mercury, then it goes to Venus, then it goes to Earth, then we have Mars, Jupiter, Saturn, and Neptune. Okay, and how do you remember the order of the planets from the sun? Well, there's a nice little clue here for you. You can learn this one off. My very excited mother just served us nachos, or this one here. My very evil mother just swatted uncle's nose. Nice little rhyme here to remember the order of the planets from the sun. Okay. Now, obviously, as you get closer to the sun here, the planets are going to be exposed to more radiation from the sun, and if we had a hypothesis about that, we would probably take an educated guess that they're probably going to be warmer the closer they are to the sun. And actually, there's one variable there that's going to affect how warm a planet is, and that is its atmosphere. Okay, so if the planet has a very thick atmosphere, it can insulate. Okay, and insulation might have two effects. It might kind of keep the heat out, or it might trap excess heat as well. So that's kind of it depends really on the makeup of the atmosphere itself. What chemicals are found in that atmosphere? Okay, you've heard of the greenhouse effect when we did climate change. The amount of greenhouse gases will be a big factor there because they absorb heat and they warm up a planet. So when we talk about planets, we should all recognize here that planets are spherical in shape. Okay, so they're spherical. All of them are spherical, and that really has to do with gravity. The gravity that forms these planets. So the planets, there's a gravitational force. The greater the mass of the planet, the greater the gravitational force, and this gravitational force has a tendency to attract the mass into the center of the planet, and it kind of over time, over a long time periods, talk about millions and millions of years, we get this kind of spherical shape. So if we had to define a planet, what is a planet, and what makes a dwarf planet different? Well, the big thing here is that again, a planet is a celestial body, so it's found outside of our own atmosphere. Okay, and it orbits a star. Okay, so they all orbit stars, and you can see that here. We have the closest planet here, which is Mercury. We have Venus. We have Earth. So it's almost like electrons orbiting a nucleus of an atom. Okay, so they're orbiting around, but they're orbiting around the star. And the reason they're orbiting the star is because there's a gravitational pull of the sun on the planets here. And the other key thing that would characterize the planet then is that it has cleared its own orbit. And that means that as the planet goes around on this orbit here, this is represented by the line, it has removed debris, it has removed asteroids and comets and meteors out of its way. And that's why we kind of represent this with a brush here, that the fact that it has cleaned or cleared its orbit. Okay, so over time, how has it cleared its orbit? Well, all of those objects in its way have been pulled in due to the gravitational force into the planet and informing the planet itself. Okay, so the Earth was just over long periods of time was formed from collisions of different objects. Okay, that created eventually a greater mass, which created greater gravitational pull, which created a planet. Okay, Pluto is not considered to be a planet because it has not cleared its orbit, even though the size of Pluto is actually quite comparable to Mercury, would be quite comparable in size. So just because the size is big doesn't necessarily mean it is a planet, and that's why it is contentious, whether people consider Pluto to be a planet or not a planet. So I've talked about that, and then if we talk about there's a few characteristics of each of the planets. Well, if we talk about the Earth, for example, the Earth has one moon. We know that it is considered to be a rocky planet. In fact, if we talk about the first four planets, Mercury, Venus, Earth, Mars, they are all rocky planets. That means that they are primarily made of rock. Okay, they have a rocky surface. And the atmosphere as well, there's a thick atmosphere present, so that's good because it means that our temperatures on our planet are maintained around 15 degrees Celsius as a result here of the makeup of our planet, which is 21% oxygen, 58% nitrogen, and 1% other gases. We are the only planet known to have life. However, maybe there's an exoplanet, which is a planet found outside of our own solar system, which contains life as well. So we don't know yet. Okay, so at this stage, I would like you to pause the video and see can you answer a few of those questions there. Right, research project, you may have done this when you were in first year, okay, looking at the properties of each of the planets. And really, I suppose the learning outcome from this would be that the fact that the planets are quite different in terms of their diameter and their mass, okay? So if we look here, the Earth, look how big the Earth is by comparison here to Jupiter and Saturn. They're absolutely enormous. And actually, one thing here as well is that, okay, Mercury, Venus, Earth, and Mars are quite relatively close to each other. However, Jupiter, Saturn, and all these planets here are actually very, very far away. There's a big order of a difference there between the distances. I'll show you something there in a while, which will represent the data there on all of those. Okay, so next what we're moving on to here is revising the moon and the sun. Okay, so in the second year we looked at the Earth, Sun, Moon system. But really we want to just learn a few things about, well, what are they first of all? So I talked here about the geocentric and heliocentric models, and we know in the present day that the heliocentric model is the accepted theory. That we know that we ourselves orbit the sun, and that's based on evidence. We orbit the sun, and it takes a year to orbit the sun. That's 365.25 days. Okay, so what is the sun? The sun is just our name for a star. Okay, it's our star. The star here, which is what we consider to be at the center of our solar system. How does it benefit us? Well, it benefits us in many ways. Like, for example, it provides sunlight, it provides heat to the planet. So that means that we don't have extremely cold temperatures on Earth. We also have photosynthesis as a result of the sun. We have wind as a result of the sun. You can relate an awful lot of things back to the sun. A lot of energy is actually derived from the sun. Okay, so that would be energy conversions that we looked at in second year. Could we survive without a star? Well, we ourselves, humans, could not, definitely not survive. But maybe there's some bacteria that could survive, because there's certain bacteria that feed on chemicals that don't actually rely here on photosynthesis, which may actually survive. So when we talk about defining the star, we could say that it's a big ball of gas. It releases heat and light, and that is due to nuclear fusion, or you could say nuclear explosions. Okay. Our moon, then, well, a moon is just a natural satellite of an orbit, of a planet, a body that orbits a planet. Okay, so the moon here, what does it do? Well, we know that it has a gravitational pull on the Earth. So if we're talking about our moon, and that causes waves. Okay, the gravitational pull, or the gravity on the moon, is about a sixth of our own planet. Remember, the bigger the mass of the planet, the bigger the gravity. The smaller the planet, or the smaller the celestial object, the less the gravity. So the moon is smaller, it has about a sixth of the gravity. What else do we know about the moon? Well, there's lunar phases, and we'll talk about that when we revise that. Okay, so with lunar phases, we know that the moon is considered to be non-luminous, but it does reflect the sun light, and that's why the sky can appear quite bright in the evenings or when it's dark, because of the moon reflecting light from the sun. So here is, and I'm not sure if this will work. This is a representation here of the Earth, Moon, and Sun. And what's interesting here is, like, to consider some of these questions here, like, when did the Earth complete its orbit? would you say the orbit of the moon is shorter or longer than the Earth? Okay, and what do you notice about the orbit of the Earth from year to year? Okay, so let's have a look here and consider a few of these questions. So if we play this here, first of all, what's interesting to look at here is that we have the path here of the Earth following along here, and as it's following along, we have days like increasing. So we are expecting here that this is going to complete its orbit, and once it reaches, a full orbit, it'll have reached 1 year. Okay, and that'll be considered 365.25 days. Okay, you notice here that actually it didn't go start back at the start, but that's because time is continually moving. So if we just started off orbiting of the Earth around the Sun, then well, that would be day 1. But here we're continuing on, so we're now on the 2nd year, and we're going on to the 3rd year shortly. Okay, the next thing then is like, well, let's have a look at the gravity. Let's get rid of the path and let's have a look at gravity. Notice here how the Sun is causing a gravitational pull on the Earth, and the Earth is causing a gravitational pull on the Sun, represented here by these arrows here. The arrows are equal in size, and that's because at the distance that the Earth is from the Sun and the Sun is from the Earth, they are causing an equal gravitational pull on each other. Okay, and that's important there, and that's why we are not being, I suppose, absorbed into the Sun, because the distance is affecting the amount of gravitational pull here that's happening on the planet. However, if we change up a few of these variables here, we might affect the gravitational pull. So let's say, for example, I'm going to increase the mass here of the Earth. Okay, notice how the arrows are becoming bigger. So we have a bigger gravitational pull here that's happening between the 2 planets, or the planet and the Sun. Okay, now what might be interesting here to compare is, like, let's have a look here at the Moon and the Earth. We're back at square 1 now again. We're back on to the 1st year. So if we look at the paths here, you can see the orbit here of the Moon around the Earth. It's happening about every 30 days. Okay, and the Earth here again is orbiting the Sun. So technically the Earth is a satellite of the Sun, and the Moon is a satellite of the Earth. Okay, and again, what's interesting to compare here is if I increase the mass of the Earth. Okay, notice what happens to the Moon. The Moon is gone. In fact, what happened there was that the gravitational pull was too much on the Moon, and the Moon collided with the Earth and became part of the Earth due to a massive collision. Okay, and so that's interesting there to compare. Okay, look, that's what I wanted to talk about there on that. So the key thing there to highlight is that as the mass of a celestial body increases, so too does its gravitational force. So it has a stronger gravitational force. Right, again, you should pause the video and see can you answer these questions. Right. Next thing we're looking at here is comets, asteroids, and meteors. Now, any videos that I see in front of me here, I'll attach them to this video tutorial. Okay, but really, what we want to look at here is what is an asteroid, what is a comet, and what is a meteor. Okay, so if we look here at comets are quite interesting in that they're in our solar system. They're mainly found in the Kuiper belt, which is beyond Neptune. These comets, what are they? Well, I think they're one of the celestial bodies that we would actually recognize, because we all know that they have like this glowing tail. And what is the glowing tail caused by? So when a celestial body, which is made of dust, rock, and ice, that comes near a star like our sun, it glows and it'll produce a tail. Okay, and what is actually happening there is an interesting physical process there, where the ice that surrounds the dust and rock, okay, when it comes near the sun, it gets so warm instantly that it undergoes a process called sublimation, which is where it changes directly from a solid to a gas. So it doesn't actually melt first, though solid to liquid. It goes directly from a solid to a gas, and it's called sublimation. And that sublimation causes a thin atmosphere here, okay, and we call this thin atmosphere a coma. Okay, so it's called a coma, and that then reflects the sunlight, which causes this glowing effect that we're used to. So when we define a comet, we say it's a celestial body made of dust, rock, and ice, and it glows, producing a tail when orbiting near a star. It should be orbiting near a star. These are often called dirty snowballs because, well, they look like dirty snowballs. Okay. Another interesting characteristic of a comet is that they have a highly elliptical orbit, which, if you compare here, this is the Mercury orbiting around the Sun. You can see it's quite circular. This is Halley's Comet, which is orbiting around here, the solar system. Do you notice how it's quite oval-like? Okay, so the comet there would have an oval-like orbit. And actually, these oval-like orbits sometimes can actually mean that they orbit outside of our own solar system and into other solar systems. So the orbit is quite different. There's another interesting video about how to make a comet and represent the model of a comet. Meteors, then. Well, what's a meteor? Well, there's two different branches here that you probably need to know. And a meteor here is technically what it is a rocky object that has entered our atmosphere, entered Earth's atmosphere. So this is a lovely thick atmosphere here. This is protecting life at all times. What it does is that actually many meteoroids, which are just rocky objects floating about in space or orbiting in space, when they hit our own planet, they enter the atmosphere, and the atmosphere burns them up. Most of them will burn up, in fact, in our atmosphere. But if anything gets through, it's called a meteor. And then once it's past the atmosphere, so past the outer atmosphere, we'll call it a meteorite. So technically, this is a meteorite. Now, they're often called shooting stars because, well, they look like a burning star when they come out of the planet. Or come down towards the surface of the planet. And well, I suppose the most interesting part of all of that is the fact that we have an atmosphere there that is burning up most of those meteoroids that enter the planet. And, why would they enter the planet? Because the gravitational pull. And why do they burn up? Because we have very, very high friction, which burns them at very high temperatures. And effectively, what's happening there is sublimation. The solid rock is actually changing directly into a gas, which is quite interesting to consider how hot that must be. We're talking about maybe 1300 degrees Celsius for some rocks to burn. So that leads us on to asteroids. What are asteroids? Asteroids are effectively just rocky objects as well. They orbit stars, but they are smaller than planets. So most of our asteroids are found in the asteroid belt in the solar system, which is between Mars and Jupiter. So thankfully, we have Jupiter there, which is actually like a Hoover of our own solar system, which absorbs in most of the asteroids. Because of its strong gravitational pull, asteroids tend to fall on Jupiter rather than us. Now, we know that there's an association there between the dinosaurs and the asteroids, so there definitely was an asteroid collision. The question is, did it kill the dinosaurs? Well, we know that dinosaurs did exist at one time due to fossil evidence, but I suppose we cannot be 100% sure whether it was the asteroid definitively that killed them. Okay, so you can just imagine a big boulder anyway floating about in space. That's what an asteroid is. How is life protected? Life is protected on Earth because it has, I suppose, a lovely thick atmosphere, which what it does is it has an ozone layer which protects us against UV light. It has this atmosphere here, the fact that it is thick and it's almost like a coat around the planet. It insulates us from really harmful things like as radiation, as I mentioned, but also extreme temperatures. The fact that when our planet rotates away from the sun, there's an atmosphere there that prevents us from losing all of that heat. That's important in maintaining the temperature there around 15 degrees Celsius on average. Well, how else is life protected on Earth because of our atmosphere? Well, it provides us with oxygen, and I suppose UV radiation, if it got through, would cause skin cancer. So that's really important that we're protected against all of that. As I mentioned, the burning up of the of celestial bodies has basically insulated life as well. I'm going to move on. This is an experiment here that you could do where you would look at elevation of a meteor and effect on the crater size. What you should find is that as the height increases, the size of the crater, the diameter of the crater increases, but only to a point because due to Newton's first law of motion, objects will reach a maximum acceleration of 9.8 meters per second, which is due to the force of gravity. Okay, so effectively, what would it mean? If it was high enough, then it wouldn't matter how big or how high the crater is. It would have the same diameter. No, how big or how far up the meteor was, it would have the same effect on the crater. So benefits and dangers of space exploration. I told you to go away and watch a TV program about this on Netflix. What's the name of that program? That's really it's quite a good program as well. Anyway, so what you should finally be able to mention here in terms of the solar system and the galaxy and space, you should be able to define all of those and really explain the benefits and hazards of space exploration. So I suppose often these words here get all confused. We have the universe, we have the solar system, we have the galaxy, but which one is which? So the universe effectively is everything. So the universe, will be look at the Big Bang Theory, but the universe is everything, okay? And underneath the universe, then you have many galaxies. So we're talking about thousands of galaxies here, and this is represented here, representing a galaxy. Here we have a solar system represented. So what is a solar system? We start with a solar system to begin with. Every solar system out there has a star, okay? And in this case, ours is called the sun. So a solar system, effectively, if we had to define it, is a star and all of the celestial bodies here that are orbiting that star, like all of the 8 planets in our solar system. A galaxy then is, if we look at it, we have all these different lights representing stars. So a galaxy effectively is just is like a system of stars. Okay, that's what a galaxy is, a system of stars. Now, Edwin Hubble, you might have heard of the Hubble telescope. He's the guy here that discovered that fact. Our solar system is not the only solar system. He discovered this back in the day by looking through quite a special telescope that was able to see further than what was seen previously. Okay, how does it all fit together? You can look at this in your own time, but there's an awful lot of relationships here. Where, like, the universe is it's infinite. It's impossible really to grasp the distances that are involved here. Space, we should know that space is a vacuum, so that means there's no matter, there's no air to breathe, there's no water to drink, there's no soil to put your feet on. It's effectively a vacuum, which means that there is no matter surrounding you. Okay, and that brings its own challenges. You have this sense of weightlessness, but like, you have to have a spacesuit because you have to be provided with your own oxygen supply. You need to be insulated against radiation, and there's other hazards as well. Like, if there's a crack here appeared in a helmet, like, you can listen to Chris Hadfield talk about it, and he says like that. You're instantly going to boil to death and experience extreme radiation from the sun. Like, it's really terrible even to imagine it. But the questions here then is, like, if it's so dangerous, why should we even explore it? Well, you should be aware here that there are many benefits and hazards to space exploration. The obvious benefits would be like technologies we developed after exploring what is, I suppose, extremely hostile territory. And because we've been pushed here to create technologies to get through this hostile territory, we have developed new technologies as a result, like memory foam. Like, you've all heard of, like, Nike Air, which has memory foam in it. So, like, that was kind of unintended technological developments here as a result of space exploration. Memory foam was originally developed for space. So insulation in houses has developed hugely as a result of space exploration, because obviously when you're out in a hostile environment where there is no matter surrounding you, then you have to be able to protect your body and make sure it doesn't experience those extreme temperatures, but also not to get extremely cold as well. Developments for robotics would be an obvious one, because we don't want to send humans to space anymore. And broadband, well, you wouldn't be able to listen to me right now if it wasn't for broadband, which is being provided for by satellite technology. The last benefit, our next few benefits there are, well, mineral resources in space, like any rare minerals here that we're kind of short of on the planet, might be more easily available in other planets or even asteroids and things like that if we could mine them. Then we want to look at the habitable planets. So there are certain planets which are out there that may be suitable for life. Okay, so that would be as our own planet becomes more populous, then maybe we could look at that. And then just really scientific discoveries for the sake of scientific discoveries, because we love like advancing and learning more. Hazards, as I mentioned, space radiation. Health, well, muscles and bones will weaken in low gravity. That's obviously going to be bad. Loneliness and isolation. Well, if you're like a million miles away from the Earth, and you're stuck inside in a small environment, it's kind of like the COVID-19 crisis, where you're seeing the same people, you're stuck in the same house. It's obviously going to have an effect on your mental health. The distance from the Earth, then, if an emergency, so like if there is, you need a health, a health check or something to see after you, then that's going to be a problem when you're that far from the Earth. So that's it. That's revision of that section. I'm going to upload notes now.